Hello students, welcome back. So in the last class, we had discussed regarding the line spectrum of hydrogen. So in the line spectrum of the hydrogen, we have seen that whenever the energy is absorbed by the electron is going to jump to the higher energy state, and that is not the stationary state for it. So when it is coming back, it is going to give out the radiations. These radiations are seen in the various region like the ultraviolet region, visible region and the infrared region. And these were observed by the different scientists. Hence, it was named after those scientists. So these radiations which were seen from any higher energy state to n is equal to 1. So here if we see that the electron jump from any higher energy state to n is equal to 1, this we called it as what? As the Lyman series. So let me consider that suppose if the electron has absorbed the energy and it is going to come down. So when it is coming down, it is radiating the energy. The emitted energy is observed in various regions. So if it is seen in the UV region, it was discovered by Lyman. So this series is called as the Lyman series. So here what happens, n will be equal to 1. That is, we consider the ground state as n1 is equal to 1. And the higher energy state, we are going to consider all these higher energy state as n2. So n2 for Lyman series will be what? It will be 2, this will be 3, this will be 4 and so on. So for Lyman series, n1 is equal to 1 and n2 can be equal to 2, 3, 4 and so on. In the same way, if we are going to observe these series in the region, that is visible region. So in the visible region, what is going to happen? n1 will be equal to 2. So in this case, what happened? The series of these lines will be from where? It will be from 3, this is 4, this is 5 in this way. And here it is seen in the visible region. So in the visible region, it was observed by Balmer. So these series are called as what? Balmer series. So in the Balmer series, what will happen? This is the ground state. That means n1 will be equal to how much? It will be equal to 2. So this n1 will be equal to 2. Then n2 it will be equal to what? n2 will be equal to 3, 4, 5, 6 and 7. So therefore in this way we are having it 3, 4, 5 and so on. So in this way we have the Lyman series, the Balmer series. Similarly, we have the remaining 3 series, that is the Paston series, bracket series and the Fund series, where n1 will be equal to 3 for Paston series and n1 will be equal to 4 for bracket series and n1 is equal to 5 for the Fund series. So in this way, we have the various lines which are seen in the different region. Now, when we are talking about the Balmer series, so Balmer conducted this experiment to show that there are the lines which are expressed in terms of wave number. Now, whatever these lines were seen in the Balmer series, so he conducted an experiment. Since it is in the visible region, this was visible to the eyes, to the naked eyes. So Balmer conducted this experiment and he showed that the spectral lines are expressed in terms of wave number. Then the visible lines of the hydrogen spectrum, they are going to obey a certain formula. So the wavelength or the wave number was expressed as the formula given by nu bar is equal to 109,677 into 1 upon 2 square minus 1 upon n square in terms of per centimeter, where n is an integer greater than 3. So here we are going to consider n1 is equal to 2 and N2 is equal to what? 3, 4, 5 and so on. So Balmer gave this formula, nu bar is equal to 109,677 into 1 upon n square, that is 1 upon 2 square minus 1 upon n square in terms of per centimeter. Now this was confined to Balmer series alone, where the ground state is equal to 2 and the higher energy state will be 3 onwards. This was generalized by Rydberg, and Rydberg gave the formula for any series as nu bar is equal to R into 1 upon n1 square minus 1 upon n2 square. Or it can also be written as nu bar is equal to 109,677 into 1 upon n1 square minus 1 upon n2 square, where R is the Rydberg's constant, which is equal to 109,677 per centimeter. So this is called as the Rydberg's constant. So this was the general equation given for the different lines in the hydrogen spectrum. So in the Balmer series, in the visible region, 4 prominent lines were observed, which were termed as H alpha, H beta, H gamma and H delta. These corresponds to the wavelength of colors, which is red, green, blue and violet. No doubt apart from that there were several other lines, but the prominent lines belong to these. So therefore Balmer gave these 4 important lines in the visible region. So this is about the line spectrum of hydrogen atom. Now based on this one, we have Bohr's model for the hydrogen atom. So Bohr gave certain explanation based upon the observed facts. So what are the postulates? Now coming to the Bohr's model for the hydrogen atom. The postulates are as follows. An atom consists of positively charged nucleus at the center, and the electrons revolve around it in a circular path of fixed radius and energy. These paths are called as orbits, or it is also called as stationary state, or it is also called as allowed energy state, which are arranged concentrically around the nucleus. So what does this mean? It means that suppose if there is presence of a positively charged nucleus, beside this positively charged nucleus there are several fixed paths. So these are the fixed path. So these are nothing but they are concentric rings, one after the other the rings are going to be there. So now what he says that there is presence of the positively charged nucleus at the center, and this nucleus is surrounded by several orbits which are fixed path, which have fixed energy and which are having a fixed radius. So here the radius and energy can be calculated. So this is how the first postulate says. Then the next postulate says that the angular momentum, which is quantized, of an electron is in a given energy state is an integral multiple of h upon 2 pi, where h is the Planck's constant, which is expressed as mvr is equal to nh upon 2 pi, where n is an integer, that is 1, 2, 3 so on, which is also given as k shell, l shell, m shell and so on. M stands for the mass of the electron, V stands for the velocity of the electron and R stands for the radius of the orbit. So this is with respect to the structure of atom of hydrogen. Particularly Bohr gave the explanation for the hydrogen atoms model. So now according to him, the angular momentum is the product of mass into velocity into the radius. So this product is called as the angular momentum. So the angular momentum of an electron in a given stationary state, means in a given orbit, is an integral multiple of h upon 2 pi. Means this angular momentum is equal to an integer. So it is a multiple of an integer of what? Of h upon 2 pi. Where n stands for what? It stands for the orbit. So therefore, the angular momentum mvr is equal to nh upon 2 pi. Now, coming to this energy states. Now here, according to Bohr, he said that the electrons are going to revolve in this concentric ring. So when they are revolving in this concentric ring, they are going to develop angular momentum. So the angular momentum is equal to what? mvr. So this indicates what? Mass of this electron. V stands for the velocity of this electron and r stands for the radius. So center to the distance in which the electron is moving. So this radius, it is going to equal to be mvr. This is equal to what? An integral multiple of h upon 2 pi. So this n stands for what? N stands for n is equal to 1, n is equal to 2, n is equal to 3. Means in which stationary state the electron is going to move. So that it indicates over here. So if n is equal to 1, it means it is the first energy level. If n is equal to 2, it means the second energy level. So in this way, this n will stand for the integers. Then next to that one, we have one more postulate which says that as long as the electron revolves in a particular orbit, it does not emit energy. If an electron jumps from lower energy level to higher energy level, it absorbs energy, and if it jumps from higher level to lower energy level, it is going to emit the radiation. That is, the energy is emitted. So what does these two mean? Means what? Here, suppose if you are going to consider this electron is going on moving in a particular orbit. When it is moving in a particular orbit, there is no radiation of any energy. When the energy is going to get radiated, whenever the electron is going to absorb the energy or it is going to emit the energy, in that case there is either liberation or absorption of the energy. So if it does not absorb energy or if it does not radiate the energy, then it will be moving in the particular orbit itself. Suppose if the electron absorbs energy, what it will do? It will jump to the higher energy state. And when it is going to the higher energy state, it is not the stationary state. So what it will do? It will emit the radiation and it will come back to its ground state. So if it is absorbing the energy, it will go to the higher energy state. If it is giving out the energy, it will come to the lower energy state. So, but in the same orbit, it neither is going to emit the radiation nor absorb the radiation when it is just moving in a stationary state. But when it does so, it will go either to the higher energy state by absorbing, or it is going to the lower energy state by emitting. Then next to that, the energy released or absorbed by an electron is equal to the difference in the energy of the two orbits and is equal to the energy of quantum of radiation. So here what happens? Whatever the energy is absorbed by the electron or which is released by the electron is equal to what? Is equal to the difference in the energy of the two orbits. As we said that the energy of these orbits are different. So the difference in the two energies is equal to the energy of the quantum of radiation. Means how much quantity of the energy is emitted, that is given by the difference in the energy of the two orbits. So that is given as delta E is equal to E2 minus E1, which is equal to h into nu, where h is the Planck's constant, which is equal to 6.626 into 10 raised to minus 34 joule second. So this constant is a Planck's constant. Remember, this is in terms of joules second. It can also be converted in terms of kg. So here delta E is equal to what? E2 minus E1, which is equal to h nu, where delta E is the difference in the energy and E2 is the energy of the second orbit, E1 is the energy of the first orbit. So the difference in the two is going to give you what? It is going to give you the h nu. So h stands for the Planck's constant, nu stands for the frequency. So in this way, the difference in the energy will be emitted or it will be absorbed by the electron to jump from one state to another state. With the help of these postulates, Bohr derived the relation to calculate the energy and radii of the stationary state of hydrogen and hydrogen-like atoms. So with the help of all these postulates, he could explain what is the amount of energy which is being released or absorbed, and he could also arrive at an equation for the radius of what? Radius of the stationary state of not only hydrogen but hydrogen-like atom. Hydrogen-like atom means what? Hydrogen is having one electron. So any other species which is having one electron can also behave in the same way. So here what we can take, for example, suppose if you are taking hydrogen, hydrogen is having only one electron. It has the atomic number equal to 1 and it has one electron. Suppose if I take helium, helium's atomic number is 2. That means it is having 2 electrons. But suppose if I take He plus, that means if I remove one electron, I am going to get what? One electron left out. So He plus is same like that of hydrogen, which is having one electron. So therefore, this is called as hydrogen-like atom. Suppose if I take lithium, its atomic number is 3. So it is having 3 electrons. So suppose if I am going to remove 2 electrons out of that, I am going to get it as what? Lithium in the +2 oxidation state. So this will have as what? 1 electron. So in this way, he considered the hydrogen and hydrogen-like atom. See, practical existence, if it is there or not, that is the secondary issue. But he gave an explanation for hydrogen and hydrogen-like atom. So let us take a look of this further things. So with the help of these postulates, Bohr derived the relation to calculate the energy and radii of the stationary state of hydrogen and hydrogen-like atom. Accordingly, the stationary state for the electrons are numbered as n is equal to 1, 2, 3, which are also known as the principal quantum number. So as we have taken here, n is equal to 1, n is equal to 2, n is equal to 3. This n is also called as what? It is also called as the principal quantum number. So first energy state, second energy state, third energy state, fourth energy state, whatever n integer we have taken, we also call it as what? Principal quantum number. It is indicated by the letter n, and we are going to consider this to be as the principal quantum number. So now, next to that one, the radii of the stationary state, is given by the formula Rn is equal to n square into A naught, where A naught is equal to 52.9 picometer. The radius of the first stationary orbit is when n is equal to 1. If you take n is equal to 1, it is the first stationary orbit, and this orbit is also called as the Bohr's orbit. So the value of it is going to come to be as 59.2 picometer. I'm extremely sorry, it is 52.9 picometer. So now let us take a look of this one. How does it mean? Now here what has happened? The value is given as what? Rn is equal to n square A naught, where A is equal to what? A is equal to 52.9. This is picometer. Picometer means what? 1 picometer is equal to 10 raised to minus 12 meter. So here A naught value is going to come to be as what? It is 52.9. So here what we are going to take? N is equal to, for Bohr orbit, n is equal to 1, means the first orbit we are going to consider. When we consider n is equal to 1, that is R of 1 is equal to n is equal to 1 square, and A value is what? It is equal to 52.9. So therefore, the value of R comes out to be equal to what? It is going to come out to be as 52.9. So this value, this R value is called as what? Bohr's orbit. Okay. This is called as the Bohr's orbit. Now, apart from this one, the energy of the stationary state is given by the equation En is equal to minus RH into 1 upon n square, where n is again the integer, that is principal quantum number 1, 2, 3 onwards, and RH is nothing but it is called as the Rydberg's constant. Earlier we have seen Rydberg's constant, but in that one it was with respect to the wave number. So we had taken it as 109,677, that is per centimeter we had taken. But here it is in terms of energy. So when it is in terms of energy, we are finding it energy, the value of R will be expressed in terms of joules. So in the terms of joules, RH value, that is the Rydberg's constant, is equal to 2.18 into 10 raised to minus 18 joules. So by making use of this equation, we can find out the energy of each of the orbit. So in the ground state, that is for example, if the first orbit, if we are going to consider this orbit, n. So for this orbit, you can consider the energy. So energy En is equal to what? It is RH into 1 upon n square. So therefore, the value of R you are going to consider, value of R is what? So the value of R is equal to minus 2.18 into 10 raised to minus 18 joules. So we are going to consider n is equal to 1. So therefore, you are going to take this as 1. So the energy of the first orbit E1 is equal to how much? Minus 2.18 into 10 raised to minus 18 joules. So this is the energy of the first orbit. So in this way, if you can take n is equal to 2, n is equal to 3 and so on, you can find out the energy associated with each of these orbit. So n is equal to 1 means the energy associated with it will be E1, this will be E2, this will be E3. So the energy is going on differing. So we can find out the energy of each of the orbit. So Bohr's theory could be applied for ion containing one electron like He plus, Li2 plus, beryllium 2 plus. So these are called as what? Hydrogen-like species. So the generalized equation for this one is what? En is equal to minus 2.18 into 10 raised to minus 18, which is a Rydberg's constant, into for Bohr's first orbit, that is ground state, n is equal to 1 we had taken, and for hydrogen we had taken where it was 1 upon n square. But if you are taking hydrogen-like atoms or species, so hydrogen-like species means what? The atomic number will be differing. So instead of taking 1 upon n square, we take it as z square by n square. So this is the generalized statement for finding the energy of different species. So En is equal to minus 2.18 into 10 raised to minus 18 into z square divided by n square joules, where z stands for the atomic number and radius for such an species is equal to what? Rn is equal to 52.9 n square divided by z. So here there will be a slight variation because of the presence of the different atomic number. We are going to make use of this z, which indicates the different atoms. So this is the atomic number. So by this equation, we can find out the energy of the hydrogen and hydrogen-like species and the radius. So this is all about today's class. So remaining thing, the problems based on these equations, we shall take up in the next video. Thank you.